All right, dudes. We're looking at phi for electrical power and P equals IV, PIV. The PIV and the VIR are the two equations that hopefully you can use when you're done with this component. So as a warm-up, I think this will help you see where we're going with power because we're going to talk about power, and here we're going to talk about electrical power. So try this out without me and turn me back on when you're ready. Okay, so Artham, no relation to anyone we know, has a certain mass that I'm estimating can run from the ground level to the science floor, which is like 8 meters change, 20 seconds. Mr. G, me, has about the same mass, but way older. It takes me a little longer because of my geriatric state. Geriatric means very old. So I want you to calculate the energy it takes Artham to climb. Well, the energy is like, or the change in his potential energy is his mass doesn't change, gravity doesn't really change, but the height changes. So you'd say, 70 times gravity's 10 times the change in height is 8, right? And so 5600 joules. That's Artem's, right? And the potential energy the energy it takes him to do that. That's the work. The work goes into potential energy. It's all the same stuff. The work. This is Artem. This is Gorkevich's work. I have a mass of 70. It's 10, and it's the same distance up, even though it feels a lot longer because I'm older. So I still have 5,600 joules of work to do to get my old body up the stairs. So what's up with that? It's the same distance. It's the same mass. You're doing the same work. It's the same energy change, right? So energy is the same. But what's different about these two is the time it takes, right? It takes me 45 seconds, and it takes Artem 20, which means he's doing the same amount of work in less time. That makes him more powerful, right? And so the power is the work over the time. So Artem's power, PA, is that 5,600 joules per 20 seconds, right? And you cancel those out and divide. And the power from Gorkevich is 5,600 over 45 seconds, joules seconds. So this would give you an output in watts. Calculator's not here, so what exact value is it? I don't know, but I do know 560 over 2 is a bigger value than 560 over 4.5. So Artem has a higher power rating because he's doing the same amount of work in less time. All right. So I want you to be able to do that sort of thing with electrical power outputs. I feel like we've been working with little fussy bits about electrical stuff, and now we kind of get to put everything together, which I like. So talking about electrical power, it's just the rate at which energy is transferred from one to the other. The rate, it's how much time it takes. Just like this, energy is transferred from chemical energy running up the stairs, from chemical energy to potential energy by work, right? So I'm doing this much work. The rate at which is how much work is changed per time. That's a rate, right? Same thing. How much work per time. That's also a rate. Guest appearance.
Hey! Did I hear the word rate?
Related rates. We're doing electrical power.
Electrical power.
Yeah, very good.
Is that related to just regular power?
Yes, and that's why we're starting with the warm-up about regular power.
Energy over time.
Energy over time. So the electrical power is just the rate at which the chemical energy can be changed into electrical energy, and that can be changed into whatever kind of energy you want.
Excellent.
Pretty
awesome.
good.
I'll let you crack on.
Cheers. So if we're trying to change electrical energy to work energy or heat energy, we want to see like how much power is dissipated. This is the equation that we're going to use, right? The power is the amount of energy that we're changing, and we talked about energy was the amount of charge times the voltage. We used this in the last section, and that's the amount of energy that we're using per time, right? That's the amount of energy per time. If you can talk about these two as charge per time, and charge per time is just current. Right? That was one of our Q over T. How much charge is moving per time is really current. So they're switching that out, and you get this equation, P equals IV. It's one that you'll use a lot. It's a PIV. So if you're trying to do a problem like this, current flows 2 amps over a 4 volt, through a resistor 4 volts across it, how much power is dissipated? You can just say, well, let's use power. I know that we're talking about the voltage and the current, and we know both of those, so you can multiply them and say, okay, 8 watts of power. Also, if you look at the units, they'll match up as well. It gets a little more obnoxious when you do something like this. What power will be dissipated when a current of 4 amps flows through 55 ohms of resistance? So I really want to use P equals IV when we're talking about power, but this is current, I, and this is resistance. So we might have to back up a step and say, okay, so basically I know I, but I don't know V. But V is the current times the resistance, so we can first run these two to find the voltage. So you'd say, 4 times 55, right? And then take that value and put it in here. So then say, power is I, that they told us, times whatever value this is. This 4 times 55. I think that's what they did here if I didn't jump the gun. Get my scribble out of the way. Cool, so they first found the voltage and then used that to find the power. Okay, there's other ways to write this P equals VI or IV. I like P equals IV, PIV. And that's, instead of using V, we use V equals IR in place of this. Insert that in there, and then you get P equals I squared R. So that's one other way to write this. Oops. And another way to write it is if you talk about the current is the voltage divided by the resistance. It's this same thing, but solved for I. You get V times V, like this is this piece. You get V times V over R, so you get V squared over R. So that's another way to write it. All 3 of these are in your formula booklet. There's P equals IV, P equals I squared R, there's P equals V squared R. Neat. All right. So let me just give you some context. This is a Tesla motor, right? Look how big it is compared to this person's hand. It's massive. It drives these cars really fast. So this can take a lot of chemical energy from the batteries and turn it into mechanical energy, like velocity, right? It can do that, change a large amount of the electrical energy into mechanical in a small amount of time. So power is the work over time. It can do a large amount of work in a small amount of time. It means it has really high power. This little tiny motor can take this same amount. It could convert a large amount of electrical energy into mechanical energy. It could convert the same amount, but it would take a very long time to do this. You could put really sophisticated gears on this thing and give it enough energy and make it drive the Tesla too, but it would drive the Tesla really slow, which makes it low powered, right? So you could take, it just takes a long time. High time in the denominator makes it low power. Same thing with like a heating element. This is like the heating element in the top of your oven. You push electrical energy through it, and it changes the electrical energy to thermal. It can change a large amount of electrical energy to thermal in a small amount of time. Therefore, it's high powered. This little light heater can do the same thing. Can take the same amount of electrical energy and turn it into thermal, but it would take a really long time. So therefore, it's low power. To give you some context. All right, 2 more questions. Current flows through an electric kettle. Here's the voltage and the amp. What's the power? How long does it take to boil? Okay, well, I think that the power of the kettle is P equals IV. We know this is I, the current. This is the voltage. And if you multiply them, you get the power. Great. That's the power. We want to boil 1 liter of water. So I need to know how much energy that's going to take. thermodynamics to the rescue. Q equals mc delta T. We know this is m. The mass of that is it could be 1 kilogram because that's the density. Boil 1 liter of water. So temperature change. They didn't tell us. That's what I was looking for up there. They didn't tell us the initial temperature, but I think they're assuming it's starting at room temperature. Raise it to 100. So this delta T is going to be 80 degrees. The mass of 1 liter of water is 1 kilogram, and specific heat is this. Right? You can look that up, or they give that to you in a formula booklet, or they give it to you on an exam if they ask this. Might be a standard question. So you could multiply those together and get the amount of joules, this many joules of energy to boil the water. And so this is 334,400 joules of energy. This thing can do 660 joules every 1 second. That's what power is. So therefore you can say, if you divide, power is energy over time. So if you divide the amount of energy with how many joules per second, you get the number of seconds it'll take, and you convert that to minutes if you want. But I think if you're here, you're good to go. You can play the same game with an electric motor, and they say I want to lift 10 kilos through 3 meters in 5 seconds. And they tell you a voltage, right? How much current flows. Well, you'd first have to see how much energy has to be output, the work done essentially. So you'd say mgh to lift this. How much potential energy are you changing? So 10 kilograms times 10 gravity times the height of 3 meters, right? So 300 joules need to go into this thing. That's great, but how much power is going to need to be done? Well, you'd need to do this 300 joules in 5 seconds. And so that's our power that we need to output, right? So there's that 305. So that's 60 watts, which is good. And then we only have 12 volts to work with. Maybe we're working with a battery. So I need to be able to do 60 watts of power. So we use P equals IV. 60 watts of power. Current, we don't know. And the voltage, we do know the voltage is 12. So divide and you get I is 5 amps. Love it. Okay, we're starting to get to use some calculations, which I like. Try it out with these, 17 through 22, and I'll see you later.